Okay, so now to conclude this exponents part for the grade 9 course, we will talk about exponential equations, and I will bring back the topic of prime and composite numbers. Okay, so what I'm going to do here is I'm going to teach you a simple fact that we can use, a logical fact that we can use, and this will enable us to solve any exponential equations question. Okay, and let's write this down. Exponential equations. Okay, under exponential equations, there are two ways in which we can solve exponential equation questions. I will discuss the first approach, and then as we progress with the course, I will discuss the other. The first approach makes use of a simple fact that, and write this down, if a to the x is equal to a to the y, then x is equal to y. This rule makes a lot more sense when we start thinking in terms of prime and composite numbers. But for now, as I said before, that there are two ways to solve exponential equation questions. The second approach is what I will teach you at grade 12, where we will utilize the logarithm function. But for now, let's just utilize the first approach that makes use of this fact. Right. Verbally what we say, and write this down, if the bases are the same, we drop the bases and equate the indices. If the bases are the same, we drop the bases and we equate the indices. That's basically what this rule says, and that makes sense logically. Right. Now remember when I taught you prime and composite numbers, I said that the prime numbers are in the simplest form. It is irreducible. And the last fact I said is that it's unique, meaning that 2 can only be 1 times 2. 3 can only be 1 times 3. 5 can only be 1 times 5. There's no other product or no other combination of two numbers that when multiplied together that can give you these numbers. It's only 1 in this number. If prime numbers are defined to be the simplest numbers, they are irreducible and unique, let's make some conclusions. You see, if I have 2 to the power x is equal to 32, and if I re-express 32 with the same base as 2, right? So basically what I'm saying is I'm trying to utilize these rules, but I'm using prime numbers to explain the rule, right? You see, if 32 in its simplest form is represented as 2 to the power 5, and if 2 itself is irreducible and unique, that means there's no other number that can represent 2 to the power 5 other than 2 to the power 5. Think about what I just said. There is no other number that can be 2 to the power 5 other than 2 to the power 5. Right? Do you understand that? So that's the reason why. That's the significance of having prime numbers, because if the prime number is unique and it's in the simplest form, then there's no other number or combination of numbers that could give you 2 to the power of 5 but 2 to the power of 5. That's basically what I am saying. So now what we can safely conclude is that the left hand side is equal to the right hand side, so therefore x is equal to 5. This is the same as this. That's basically what I am saying. Understood? So let's do another example. Let's say we have 3 to the power of x is equal to 27. Then 3 to the power of x is equal to 3 cubed. And if I look at this here now, I can say that there's no other combination of numbers that could be 3 to the power 3 than 3 to the power 3. It can only be 3 to the power 3. Therefore, we can say that this is the same as this, so therefore x is equal to 3. Now, I must state that this rule, this logical rule, did not state that the bases have to be prime. I just use prime bases to explain the rule. Let's say if we have 4 to the x is equal to 16, then what I can say is that 4 to the x is equal to 4 squared, therefore x is equal to 2. Right? The bases just have to be the same. It does not have to be prime bases. I could have very well made this a prime base, made that a prime base, and use the logical thought of the prime bases being unique and so on. Right? I could have done that. But according to the rule, we can just use the bases if they are the same. Understood? We can just equate the indices if the bases are the same. Right? So let's say we were given another example. Let's say we were given 2 to the x, 3 to the y is equal to 2 to the power 5 times 3 to the power 3. Then what we can conclude is that x is equal to 5, right? And y is equal to 3. Why? Because there is no other combination of numbers that can be 2 to the power 5 but 2 to the power 5. So therefore we're saying that this is the same as this, and this is the same as this. Understood? So even though we have a product there, we can segregate it like this. We can segregate it and create two equations. And this is what's very fascinating about this fact of using prime numbers and them being unique, is that there's no other combination of numbers that could give you 2 to the power 5 than 2 to the power 5. And that is why x will be equal to 5. Understood? 3 will not even be in there. Think about that. Think about that. 3 will not even be a factor in here because it's only made up of 2's. And if 2 is just 1 times 2, there'll be no 3 in there. Understood? Because it's unique. It's in the simplest form. So therefore we can say x is equal to 5. If we look at 3 to the y is equal to 3 to the 3, then we can say that y is equal to 3 because we know, we can rest assured that 3 to the power 3 cannot be represented as a product of 2's, or there will not even be a factor of 2 in 3 because 3 itself is a prime number and 3 is unique. So therefore y has to be 3 and nothing else. This was the grade 12. The grade 12 question wasn't phrased like this. It was slightly more complex, but I just refined it and I just took the more easy part from it so that you could see exactly what we are talking about. Okay, so that's basically what I am saying. And that concludes this part of the exponential equations questions. And exactly how, let me just re-emphasize, the bases just have to be the same. They do not have to be prime bases. But I use the logic of prime bases to explain the rule. Okay, but the bases just have to be the same. Okay, that's about it.